Hello, everybody. My name is Luiz Carlos Cotovitz Jr., and I am visiting professor at Labomar, Institute of Marine Science at the Federal University of Ceará. I am very glad to be here to continue our very important event, the third Fortaleza Austral Spring School, and we will continue speaking about anthropogenic impacts on the ocean, in the coastal and the ocean. And for this afternoon, we will have more three speakers, Dr. Paolo Orta from the Federal University of Santa Catarina, Dr. Vanessa Hatje from the Federal University of Bahia, and Dr. Luiz Drude Lacerda from the Federal University of Ceará. If you have any questions to speakers at the end of the presentations, we have time to discuss, to pose a question in a round table. When you can discuss and pose questions at the end of the presentation, then we have the three presentations, and after we have time to discuss and pose questions. I am very glad then to be here to present the first speaker is Dr. Paolo Orta. Paolo Orta is a biologist with a doctoral degree in biological science at the University of São Paulo. He made postdoctorate in marine ecology at the Plymouth University and University of Algarve. Now, Paulo is an associate professor at the Federal University of Santa Catarina, where he's teaching, works with undergraduate and graduate problems in the areas of marine ecology, seaweed ecophysiology, taxonomy, phylogeny, and biogeography. He is a coordinator of projects related to environmental impacts and the whole of climate change and marine pollution on the coastal and open ocean. Then I would like to thank you very much, Paulo, for that you are here with us, and you can start now your presentation. Thank you.
So I must say thank you for the organization. It's really a pleasure to me to be here and share a bit of what we produced in the last couple of years, and of course about a bit about our concern regarding our future. So thank you very much. I think this is a very interesting alternative of meeting people abroad and build bridges like that between Italy and Brazil. This morning I was wondering about this beautiful and blue ocean we have between us, and the talks was really very nice. So in my talk, we're gonna talk about the problem we have in our hand right now. The Anthropocene is changing everything. So we will focus in the characterization of this actual condition, the description of everything we have in Southwestern Atlantic. And in the end, we will talk about very fastly about solutions, potential solutions, just to provide some good perspectives for the next years. Well, we are facing maybe a moment in our planet that we never thought before. After years of development, this is the global total production, total income that is rising from 1850s, more or less, and rising with exponential scale. If we are producing money, we are producing richness for people, or for few people. In fact, we are producing a huge transformation in our lands and seas. Well, agriculture is something that we was not discussing this morning, but I think we must pay attention on that. Agriculture, mainly in South America, is transforming more than half of our lands, considering the production of crops. So in agriculture, you use fertilizer, we use herbicides, we use pesticides, we use toxins, different toxins, that this is changing not just the surface of our lands, but also the waters, and the waters that is running through our continental and the continental mass, and to going to the oceans, and mainly to the coastal areas. Well, the last decade we expend, of course, a lot of effort trying to synthesize what we know about our diversity. We passed through the decade of biodiversity organized by UN, United Nations. And through this period of time, we went deep in everything we know about different kinds of environments. We are talking about mangroves, coral reefs, seagrasses, different kinds of forests we have underwater. And all of them are in very intimate, very close relationship with man, human being. Of course, with our cities, our harbors, everything we do in our coastal areas are interplaying with human being in different aspects. This produce, of course, a map of concern, considering the anthropogenic threat we have mainly in coastal areas, as we can see in this map in the high corner. We see in blue, of course, the blue and gray, the terrestrial problems or threats, considering the bars here, high levels and low levels, if it's below or going up. So as we can see, we have threats everywhere in this planet. Terrestrial and marine environments need to deal with pollution, need to deal with human uses, need to deal with alien species, invasion by invasion, I mean, and of course, we must talk about it, they need to deal with climate change. So the cumulative map that we provide here, I'm trying to reinforce more what we have in Southwestern Atlantic. We can see this area going to warm colors in this coastal land and sea regions from the south of Brazil going to the northeast. And we have something around ready everywhere. What that means? That means that we have problems everywhere related with climate change, human use, human population, mainly in southwestern and south of Brazil and southwest of Brazil. The population, of course, is a major problem in the north, but here in the coastal area is a huge problem too. And of course, we have alien species. We have the sun coral, we have seaweeds that are invaders, so we have different problems in our seas considering bioinvasion. So we have a perspective, I think, that we must pay attention on it too, that we have a huge planet. However, it isn't. We have a very thin atmosphere that can provide conditions to life. And this amount of air and water we have in our surface, very thin layer of air and water, I must highlight, well, are changing. It is changing fast. Here we have an animation just to realize why it is changing so fast. We are burning things that needed some thousand or millions of years to be produced, to be transformed. I mean, with using sunlight, algae, trees transformed CO2 in oil, in coal, in things that we are burning to produce energy and to move our cars and trucks. So we have more than 1 billion of cars in our planet, of course, billions and billions of tires, and of course, we are burning to move all of that, thousands and trillions of oil barrels or tons of coal. So now we can understand when we go to our cities in São Paulo, in Fortaleza, or even in Roma or big cities in Italy, we have huge traffic, rush times in the end of the afternoon. Then we realize what is going on. So we are changing everything. We are warming our planet. We are heating it in very fast in this last years because the oceans can't sustain the heat anymore. So we are losing our equilibrium. And this is equilibrium is very important to keep our life. So we are jumping in a pot or in one aquarium in one mesocosmos that we have no idea about what we have there. And the cost of that is high. I did a very, very fast.
Hi, everybody. Hello. I think that you have a problem of connection. Then we will wait some minutes to wait Paulo to come back here and continue the presentation. Sorry for this technical problem, but this type of event online, sometimes we have these problems. Hi, I'm back. We'll move to the second presentation, the second speaker, because Paulo have problems with the connection. Then we'll move to the second presentation, and then after Paulo will continue the presentation at the end. Then I will present the second speaker is Dr. Vanessa Hatje. Vanessa is oceanographer with a master's degree in geoscience at the Federal Fluminense University and a doctoral degree in chemical oceanography at the University of Sydney, Australia. She made postdoctoral at the Federal University of Bahia, and now she is an associate professor at the same university. The research of Vanessa focuses on the biogeochemical cycling on trace elements and influenced by natural and anthropogenic drivers. Her research group developed new techniques to detect trace metal, including rare earth elements and organic contaminants in marine matrices. She applies these novel and persisting methods to better understand the factors affecting trace contaminants in the ocean, transfer of materials at the continental ocean interface, and interactions with biotic and abiotic components in the coastal ecosystems. Then I would like to thank you, Vanessa, for your here with us, and thank you. You can start when you want.
So thank you, Luis. I would like to start saying that I'm really happy to be here and thank the committee for the invitation. It's a good opportunity to be here talking about trace metals, a little bit of the GeoTraces program, and a bit of the work I do as well. So, Abraham, if you can start with the presentation with the first one. First slide, please. Okay. So, next one. So this talk I organize in 4 sections. First, I'll give a brief introduction on trace metals. Then I'll talk a little bit about the human footprint in the ocean. I'll move to the ocean decade, particularly thinking on the clean ocean output. And then I'll wrap it up in a summary. Next, please. So, we all know that when we talk about the ocean, we have to keep it in mind that it's a large, deep, remote, and often a hostile environment. And it provides numerous ecosystem services, including food provision, climate regulation, habitat services, cultural services, and biogeochemical cycling of nutrients, connecting coastal, surface, and benthic realms of the ocean, promoting the sequestration of carbon. Well, but the pressure of over 7.8 billion people is leading to cumulative and synergic effects that have the potential to degrade the quality and resilience of ecosystems. So globally, the ocean is being treated as a waste sink, mostly due to our propensity to view dilution as the solution to pollution. Next, please. So when we talk about contaminants in seawater, we have to remember one of the most well-known characteristics of the oceans, which is the water is salty, right? So around 35 grams of salt is dissolved in seawater, and the constituents of the common salt, sodium and chloride, make up more than 90% of this dissolved mass. If we add only 3 more elements, calcium, manganese, and sulfur, we reach to 99% of the salt composition. And with only 3 more, we reach up to 99.9% of the dissolved mass in seawater. Yet, there are more than 80 other naturally occurring elements, and all of them are found dissolved in seawater, sometimes at extremely low concentration. So it's very tempting to think that these other elements are at such a low concentration that they simply do not matter. So here we can see a color-coded periodic table indicating their concentrations. So in green, in this first row, we can see the transition metals, say zinc, iron, manganese, which are necessary for our good health and that occur in very low levels in the ocean. We can also see further down this table elements such as the rare earth, which are my favorites, that are even less abundant and well known. Next, please. So the immediate consequence of their low-level concentration in seawaters is that the study of the chemistry of the ocean is strongly dependent on specialized ships with clean sampling systems and analytical tools. It's a phenomenal analytical challenge to measure elements at such low levels in a matrix with high ionic strength on samples recovered from kilometers below the ocean surface and on ships made of metal that represent a huge potential source of contamination. So despite all these challenges and the low concentrations of the trace elements, they are fundamental to the functioning of the ocean. Next, please. So similarly to us, phytoplankton and other organisms need nutrient for several biogeochemical processes. Can you press again, and one more? Yeah, that's fine, thanks. So as you can see here in this phytoplankton cell, we need trace elements to uptake carbon, phosphorus, nitrogen from the seawater. And inside each of these phytoplankton cells, and for all other organisms in the ocean as well, so there is an important participation of metals in a series of proteins, amino acids, and biochemical processes. So now that we know that the oceans have a number of trace metals, and most of them come from natural sources, such as rivers, dust, submarine water discharge, and more recently, we discovered the importance of hydrothermal vents for the input, for instance, of iron and manganese. We actually can see another one, please. We can actually, yeah, that's fine. We can actually, we actually know today that inputs from hydrothermal vents can release ion that can travel up to 4,000 kilometers. So it's a very important source that we didn't know a couple of years ago. Next, please. Yes, that's fine. However, metals in the ocean may also derive from anthropogenic activities that can discharge mostly benign elements such as iron, but another one, please. But also contaminants that may cause harm to the entire ecosystem, such as mercury. Next. But why we care about these trace elements, okay? It's partially because they can act in several ways that interest us. One of the most important roles already mentioned is that trace metal act as nutrients, but they can also act as proxies, as tracers, and so we can use these elements to understand the circulation of the ocean, the past productivity, and so on. And these metals can also work as pollutant, as we shall see. So many anthropogenic changes in trace elements and other pollutants have been unintentional and are associated to climate changes that results, for instance, in extreme events, in changes in runoff, changes in river inputs, and also in pH and oxygenation. Other changes, not so much, as you can see. Next. So here we can see an infographic that I'm working right now, but this very preliminary version already shows that we have a lot of human drivers that pollute the ocean. We have, for instance, ocean and continental mining, we have industries, we have burning of fossil fuels, we have fisheries, urban runoff, besides agriculture, sewage inputs, and so many other sources. But not all metals get to the ocean by each of these sources. Plastics, organic contaminants, pathogens, light, noise, exotic species, they also do. They are also associated to anthropogenic activities. And they may lead to many effects in biota, such as change in biota communities, immigration of organisms, mortality. Can you go back one slide, please? If you wait, I can tell you next, and then you move. Thank you. But the adverse effects, the pollutants may also impair ecosystem services, causing loss of habitats, seafood contamination, decrease in biodiversity, reduction in climate regulation ability, among others. Next. So among the metals that are contaminants in the ocean, one of the largest concerns is mercury. Mercury reached the atmosphere by the input of burning of fossil fuels, mining, and industrial activities. After being deposited in coastal and ocean waters, they are taken up by phytoplankton, small fish, medium fish, large fish, at the top of the food chain. So mercury is transferred to the food web, and the concentrations are biomagnified. And then, because we consume all these top predators, we are exposed to the metal contamination ourselves. Next. Among the metals, there are contaminants in the ocean. The ones that, apart from mercury, that are of greatest concern is lead. And it's a good example to see how the man has changed the metal cycles a long time. So look at this graph. So since the Roman period and at its peak, the Roman Empire probably used 80 tons of lead annually. It has been estimated an annual lead production during the first 2 centuries of approximately 4 kilograms per capita, which equates to 2/3 of the annual per capita lead consumption in the United States during the 70s. As a consequence, lead and mercury pollution related to metalworking and the production of weapons within the Roman Empire between 600 BC and 300 AD, as you can see highlighted here in red, was so intense that the concentration of these elements in the troposphere increased globally and was recorded in Greenland ice, as we see here. Next, please. Thank you. So the US Clean Air Act of the 1970s was a really important mark, as you can see in this graph in the left. What it happens here is that there was a mandate to reduce atmospheric pollution, which required the removal of lead from gasoline. But look at this top panel on the right now. Lead in surface waters began to rise from about 10 picomolar per kilogram at the beginning of the 19th century with the development of the US Mississippi Valley Lead District in the mid-800s and the US Industrial Revolution, reaching a plateau of about 80 picomolar per kilogram in the 1920s. Seawater lead concentration began to soar in the late 40s, with the end of the World War II, rising US prosperity with the motto, 2 cars in every garage, that obviously was run on leaded gasoline. And eventually, European prosperity. So surface ocean lead peaked at more than 200 picomolar in the 70s. But since then, Western North Atlantic concentrations have fallen continuously, with the lowest surface water concentrations observed so far, around 20 picomolar per kilogram, seen in one of the US Geotraces North Atlantic cruises in November 2011. Next, please. So here we can see in the right-hand side panel how the profile of lead in the North Atlantic changed from the late 70s up to current date. We saw super high concentrations initially at surface, and as a result of the emission reduction, the surface concentration started to decrease and the peak concentration started to travel to deeper waters. So look now to the panel in the right. It shows the 2010-2016 snapshot of the distribution of dissolved lead in the Atlantic Ocean obtained by geotrace cruises, and also illustrates how contaminants are useful tracers of the ocean circulation patterns. Because lead has a residence time in the ocean of around 2 years, say, near surface waters, to about a century in deeper waters, this distribution was quite different in the 1980s, with the highest concentration at that time near the surface, as emissions from North America and Europe peaked in the 70s. In the 2010s, the highest Atlantic lead concentration are seen in the waters that sunk from the surface during the period of peak emissions. As a result, in the decade of 2010s, in the North Atlantic, the highest lead concentration are seen in the Mediterranean outflow and the Labrador seawater that sunk in the decades around the 70s. The water is now concentrated in the eastern North Atlantic at the depth between 1,000 and 2,000. And it has been replaced by more recent Labrador seawater that carries lower levels of anthropogenic lead due to the major emission reductions upon the elimination of the leaded gasoline consumption. Although the deepest waters of the Atlantic still have low lead concentrations, their isotope signature demonstrate that they originate from human activities. Next, please. But the development of the modern mass spectroscopy methods has promoted the growth of the research related to contamination of the ocean. The innovative techniques developed allow the identification of new group of contaminants for which reliable quantitative estimates of environmental pathways, loads, and concentrations in the ocean are still lacking. There's the case of the technology critical elements that including the platinum group elements and most of the rare earth elements that are essential components of a range of applications, including defense, medical, and clean energy production. So the norm range of high-tech applications make them mobilize from few mining areas in states, in China, even in Brazil, where they are abundant, to be distributed worldwide. Next, please. Among the rare earth, the most widespread human footprint in marine water is the occurrence of the anthropogenically derived gadolinium. Gadolinium pollution was first reported in rivers that, excuse me, can you hear me okay? I'm just got, Luis, can you hear me okay? Can you just say...
Hi, Vanessa. Yes, I can hear you. Yes,
okay,
it's
because
okay.
I just saw a message here and I didn't understand. Okay.
But, okay.
Okay, so where was I? Gadolinium. So, so gadolinium has been used worldwide for as a contrast agents to increase detail and clarity of diagnosis. And because it's very resistant to degradation and it's very refractory to process of wastewater treatment, it's being released in large quantities to the environment. Can you go to the next slide, please? So here we can see in red the inputs of anthropogenic gadolinium in coastal waters of Salvador. So the gadolinium anomalies have also been observed in seawaters of Japan and the North Sea and California, as shown here in this graph, when you can see the normalized concentrations of the rare earth, and you can see peaks in the concentration of gadolinium, indicating there's a positive anomaly from anthropogenic sources. Next, please. So the platinum group elements, metal associated with plastics, plastic themselves, trace organic contaminants from sunscreen, for instance, are huge challenges that require hard analytical work to be measured. And these potential pollutants are not alone. The better we get in terms of analytical techniques, the higher the number of contaminants we will find in the ocean. So next, please. So looking ahead at the objectives of the United Nations Decade of Ocean Science for Sustainable Development to be held between 2021 and 2030, specifically regarding the outcome clean ocean, we have a lot of work to actually achieve the clean ocean we want by 2030. Next, please. But what do you really mean by clean ocean? So clean ocean is an ocean where all inputs of pollutants are minimized and do not have adverse effects on physical, chemical, and biological processes, ecosystem functions, and services. It will be critical to increase our understanding of the coastal and ocean systems to fulfill the knowledge gaps, identify priorities for future research, and develop solutions to promote ecosystem and human health during the ocean decade. Next, please. So some of the gaps and priority actions for the ocean decade when thinking about clean ocean outcome should be to determine the pollution status using, of course, the ecosystem approach. We also need to determine a source inventory and actively reducing emissions of pollutants. Third, we need to determine carrying capacities of areas of ecological importance. Fourth, we need to promote the integrated management of the coastal and marine zones. These are not easy tasks, and obviously this list could go on and on. Next. So, in order to succeed and achieve the goals of the ocean decade, we need to expand the analytical capacity and expertise at personal and institutional level. These capabilities are extremely uneven across Brazil and also along all South Atlantic. We need to develop and apply common procedures, implement strict quality assurance, quality controls, and build open data repositories for the whole community. We need to increase the network of collaboration, identify strategic partnerships. Together, we are stronger. Obviously, we need to reduce emissions of all sorts of pollutants. And if you are to have a clean ocean, we need to expand the wastewater treatment system and develop cheaper technologies for waste treatment. There will be no clean ocean without seawater treatment, as simple as that. Lastly, we need to integrate social, economic, and natural sciences in the development of public policies. Next, please. So in summary, climate change and environmental contamination are continuing and will be enhanced by human activities impacting ocean chemistry. Monitoring of trace metal cycles and other pollutants and novel approaches to assess the interactions with ecosystems will be required to assess how ocean responds to these stressors. The challenges of identifying, reducing, and eliminating the input of pollutants that threaten human life and the ocean are obviously global, but actions need to be local and regional, considering the particularity of each region. Marine geochemists are well placed to address this challenge. The revolution in the understanding of trace metal cycles and other pollutions that has occurred in the last decade has been enabled by new technologies, including those to sample the ocean cleanly, to make rapid and accurate measurements at low concentration, and to model and interpret results. Technological advances continue. Chemical sensors for some critical metals are now seeing application in coastal environment and will soon reach detection levels at which open ocean deployment on autonomous platforms such as cargo floats or ocean gliders become possible. This will enable trace metals to be mapped at unprecedented temporal and spatial scale. Other exciting advances are starting to come from combining studies of pollutants with genomics and proteomics in seawater. Such work will provide radically new information about how species and ecosystem respond to metal availability. New genetic sequencing approaches with associated data handling are allowing us to link microbial community diversity, structure, and functioning to ocean chemistry. So, fundamental new understanding of the linkages between pollutants, ocean, and human health that will arise from the ocean decade will help scientists to assess the impact of global change on the whole ocean climate system and inform policymakers about society's future interactions with ocean. So the solutions are there, but it will only achieve the ideal benefits if they are built on the basis of robust ocean science designed jointly by all stakeholders. Next, please. So I'd like to thank for the invitation to be here and for the attention of everyone. And I'd like to invite you to check the GeoTraces webpage and the webinars that you can find in this page, and also invite you to check the Ocean Decade page that the Ministry of Science and Technology is putting forward for us. Thank you very much.
Thank you very much, Vanessa, for your fantastic presentation covering so many aspects of the trace elements in the ocean, from the laboratory analysis to the human footprint. At the end of the presentation, we'll have time to discuss more about this and pose questions, of course. Paolo Orta is still having problems with connection. Then we will follow with the third presentation, and after Luiz Drude, that they will present now. After, at the end, Paulo, if he establish the connection, will come, you present. Then I will present Luiz Drude Lacerda. Luiz Drude is a biologist with master and doctoral degree in biological science at the Federal University of Rio de Janeiro. He's a full professor at the Federal Fluminense University and full professor at the Federal University of Ceará, at Labomar Institute of Marine Science. He's member of the Brazilian Academy of Science, and he is also fellow of the World Academy of Science. He was visiting professor at Hamburg University in Germany and Toulon University in France. He has coordinated several important scientific projects with extensive international collaboration, including the Millennium Institute of Transfer of Materials at the Land-Ocean Interface, and the National Institute of Science and Technology of Transfer of Materials at the Land-Ocean Interface. He was member of several scientific committees at national and international programs, and at the moment, he's a scientific director of the Ceará State Foundation for support of scientific and technological development. He has a strong experience in the area of ecology, with emphasis on biogeochemistry and environmental contamination, acting in the many topics, including coastal environments, environmental contamination, metal pollution, biogeochemistry, biogeochemistry of tropical ecosystem, and global change impacts on coastal and open ocean waters. Thank you very much, Drude, for you here with us, and you can start your presentation. Thank you.
Yeah, thank you, Luis. It's a pleasure for me to be here. I hope you are listening well. My voice is not very good today. I'm not COVID, but a very strong flu. Anyhow, I'd like to thank also Labomar and Professor Sergio Rossi that invited me for this talk. It's a pleasure for me, since I'm out of classes for so long. I'm actually working, as Luis said, on the local support agency for research in science and technology. So it's a very good opportunity to be back on class and give a lecture. I'm going to talk a little bit differently from the others of a subject that has been called by many different scientists all over the world, either as our legacy of pollution or our next chemical time bomb, meaning that humanity has been quite irresponsible for many years and centuries before taking into consideration controlling pollution. In the end, although most of pollution sources are well controlled and technology has cleaned a lot, we still have a huge amount of pollutants distributed throughout the planet. And obviously, these pollutants that's being, as Professor Hatje has said, is being emitted to the planet since the Roman time, probably even before that, is accumulated under the normal conditions you found in the planet. Except for one thing, these conditions are changing and changing fast. So all the equilibrium that this deposited pollutant has reached can be broken. And I'm going to talk about some examples of this phenomena that is already occurring throughout the planet and the risks associated with that. I will concentrate on three different environments: the Arctic, the Amazon, and the semi-arid coast. If you think about these three areas in the planet, they can be considered extreme environments. The Arctic, as you know, frozen most of the time. The semi-arid coast, nearly without rainfall most of the year. And the Amazon, that thrives in a very, very strict equilibrium between life and death. Unfortunately, nowadays, more close to death than life due to irresponsibilities of our unfortunate federal government. So I'm going to talk about these three environments because most of the impacts from global warming are more easy to identify and measure in extreme environments. This is a conclusion that came out of one of the first reports of the IPCC. If you look for any, in this morning, we have a very good presentation by Professor Patricia Ziveri that show many global maps, and Paulo, in the beginning of his presentation, also showed interesting global maps when it's quite clear that all the effects of global changes, particularly global warming, occurs more intensively in these extreme environments. So this is one first thing. The other thing is that global scale pollutants, those pollutants that can migrate throughout the globe, like many gases, like CO2, but like mercury also, tend to suffer these effects more easily than those locally derived pollutants. It is more to a regional or local problem. Also, another important thing is that anthropogenic regional and local drivers impact to maximize the impact of global change. And we're going to see this example, which is very clear in the Amazon and in the semi-arid coast. Another aspect is that mobilization of any contaminant increases its bioavailability because they change chemical stability and become more bioavailable. And therefore, this will threaten both human health, or food security, human health indirectly through contamination of food. Next, Abraham. So let's start with the Hatje. The Hatje is probably making the last 10% of Nature magazine cover and most of newspapers worldwide because of their extreme impact of global warming on the Hatje. It's very easy to compare year by year the diminishing of the sea ice. Major drivers of pollutants are linked to these impacts on the continent mostly, basically by increasing continental runoff, either by glacier melting, defrosting of soils, and this is a very, very important thing. Most of the permafrost is being liquefied and releasing not only CO2 to the atmosphere, but also anything that's being accumulated there. And these soils are thousands of years old, so they have thousands of years of metal accumulation, for instance. Increasing continental runoff because of increasing river flow, strengthening thermal stratification in the sea. There's another aspect that has been shown by Professor Patricia in the morning, which is very important because stratification changes chemical speciation and therefore bioavailability, basically through the induction of redox reactions that normally wouldn't occur in an oxidized environment. And this can result in increasing productivity and organic carbon production. And this is, again, an example of the interaction between local, regional, and global events. The increasing productivity in organic carbon that has been highlighted by Paulo just in the beginning of his presentation is due mostly to agriculture. Next, please. Well, as you can see in the right corner, the high right corner, you see that global warming in the average atmosphere is about 0.8 degrees Celsius. When you move to the Arctic, this average goes to 5.6. So this is the reason, basically, that the Arctic is changing so fast. I mean, 5 degrees Celsius changes completely the equilibrium between ice forming and the icing. And another aspect you can see in this picture, there's a very good review of the impacts in the Arctic. You can easily see the immense auments of continental runoff to the Arctic Sea. And continental runoff brings pollutants. Next, please. So that's a very common thing that is occurring in the Arctic, and it also occurs, and we're going to see later, in the semi-arid. Those rivers that nearly were most of the year blocked by sea ice, they are running free to the ocean, bringing huge amounts of pollutants. This is a typical hydrological curve of one Arctic river, one of the major Arctic rivers, the Mackenzie River. And this is very typical of the impacts on extreme events in these areas. I mean, global warming can easily affect and do affect the Amazon River, for instance. But in a river that presents an hydrological curve like this, the impact is huge. The next one, please. As a result, just in the first graph, you can see that runoff increases by orders of magnitude from a very short period of time. We're talking about from the late 60s to today. So there's half a century maximum. And the result of this increasing input of metals to the Arctic Ocean is a consequent increase in metals in the biota. And those two graphs below, you can easily see the increase in mercury concentration in different organisms in the Arctic Ocean. And this is, again, only from 1997 to 2010. So we are talking about a very, very fast phenomenon. It's occurring never before in the planet. The next one, please. In the Amazon region, the situation is the same. I mean, you can easily consider the Amazon as another extreme environment. I mean, not because of environmental characteristics, like in the Arctic or the semi-arid, but because of the very fine equilibrium between the biota and the physical and chemical environment. And this is being destabilized by many human actions upon oppression from global warming. So again, what you see in the Amazon today is this increasing runoff due to increasing Andean glacier melting, increasing soil temperature, and this increases the re-emission of gaseous species of many pollutants, mercury, for instance, but also VOX and any other organics. Lakes are experiencing an extreme of thermal stratification. And this is very, very important because due to the extreme dry seasons that is presently occurring in the Amazon for the past 3 or 4 decades, we never have such dry season like we see today in the Amazon. This stratification is very easily broken because the level of lakes drops so much that wind forcing is able to mix the water. And when it does that, it makes many substances produced under redox conditions, including a lot of pollutants such as methyl mercury, for instance. And this is very rapidly accumulated by the local biota. So increasing redox reactions is a very important thing occurring very fast today in the Amazon. And deforestation, as I said, is a regional thing that has nothing to do with global warming, but the impacts of deforestation under a global warming scenario is huge, much higher than it was before. Next one. And again, exactly like in the Arctic, you can easily see the results of these changes on the mobilization of pollutants. So this is a slide of the Amazon region. Just this is the picture. Unfortunately, the map is 2 years old, so it will be much more yellow than it's today, unfortunately. But this is to show you the atmospheric deposition, natural atmospheric deposition of mercury over the Amazon. So during the 10,000 years of its existence, it received mercury from the atmosphere. Soils in the Amazon, in the forest, the intact forest, accumulate anything that comes from the atmosphere. And this is also a strategy for keeping the forest alive. So natural soils in the Amazon tend to be very enriched in mercury. Mercury easily complex with organics, and the podozolization of these soils, which is very intensive, accumulates mercury in the surface of the soil. Again, the next one. So what happens when you take the forest out under a scenario of climate change? Obviously, this would occur with or without global warming. Global warming, in this case, just accelerates the process. This is a little complicated cycle, but I will just point the most important thing. When you have the forest, the intact forest, most of the mercury that comes into the forest is accumulated in the forest soil. Yeah? A part of it is exported back to the crown, it circulates in the crown and comes back as litter fall or fruit fall and accumulates in the soil. Then you have a very large amount of mercury in forest soils when you compare to soils without forest. In fact, about twice the quantity you have there. When you take up the forest, the first thing that occurs is you lose the topsoil. And the topsoil brings a lot of mercury to the rivers. So while in the forest you have over 24 milligrams per square meter of mercury, when you go to a soil without the forest, this drops to half of it. So half of it is being lost to the rivers. But also, a large portion, because of the increasing temperature of the soil, is exported back to the atmosphere and exported through the atmosphere, enlarging the area affected by this process. The next one, please. So this is the clear effect when you analyze forest and pasture soil. You see that forest soils has much more mercury than pasture soil. And this is the same place. I mean, they receive exactly the same mercury. So it's not that the forest soil has more mercury, it's that pasture soil has less mercury. The next one, please. And what is amazing about this is that this is, when you think about that qualitatively, you understand it pretty well. But if you think about the Amazon, like Vanessa said about the oceans, they are huge environments. Any modification to change chemical behavior or chemical loads has to be very large. Otherwise, you're not going to see anything about that. For instance, if you go to a river like the Madeira River that it's in this, which is the major contribution of particles to the Amazon River and there to the ocean. I mean, I'm talking about a river of nearly 70,000 cubic meters per second of flow. In this area, the river has normally 80 to 100 meters deep. So we are talking about a huge thing. To change the chemistry of this water, you have to have a huge process. Otherwise, you're not going to see it. And most of this occurs in the basin of the small tributaries of the Madeira River, where most of the forestation occurs, where most of the forest soil interaction is stronger. And again, the next one. And you can see that this process that is that I talked before about exporting from soil and the gassing. The next one, Abrão, please. Again, this is just a very short period from 2010 to 2020. 10 years of monitoring, 4 times a year. A huge, boring work, but it's the only way to see that things are really occurring very fast. Think of changing the chemistry of any substances in a dilution effect of 70,000 cubic meter per second of flow. If I start trying to calculate it by year, I'll take some time of my 30 minutes to do this. But you can imagine the huge amount of dilutant, in case water and particles. The Madeira River can have up to 1 gram of suspended material. Notwithstanding this, when you monitor the last decade, the export of mercury and methyl mercury from the river is increasing. And it's increasing not only in amount, because you can say, well, the Andean glaciers are melting, so what you actually increasing is the flow of the river, not the mercury. No, this graph is the ratio between methyl mercury and mercury. So you are changing a different correlation between elements, in case 2 contaminants, because you are remobilizing it. Methyl mercury is not produced inside the Madeira River. It's produced in the forest soil and in the small tributaries that has the chemical condition that allow it. So when you see it, and you see that you solve it mostly, the increasing mercury transported by the river is huge. We are talking about tons of mercury. Just as Vanessa talked a little bit earlier, we are talking about the global annual production of mercury being transported by the Madeira River in 1 single year. And methyl mercury probably much more. So we're talking about tons of mercury and kilograms of methyl mercury. So we are not whenever I talk in certain audiences of these problems, people say, well, this is an academicism. It obviously it does occur, but it has no actual meaning. Well, those people are wrong. The meaning is there. I mean, we're talking about huge amounts of contaminants being remobilized. And the effect is quite simple. If you get a fish in the Madeira River today, it has much more mercury than it had in 1985 when the gold mining exported over 100 tons of mercury to the river. So this remobilized mercury is actually changing the quality of the fish and affecting food security. Next one, please. Then we go to the semi-arid, which is quite a different environment, but also an extreme environment that is suffering a lot. And then you can see, for instance, the decrease in annual rainfall in that small little figure. First one. Again, another important thing is the frequency of extreme droughts. If you go to the 16th century, extreme droughts occur maybe one or twice per 50 year. Nowadays, 12 per century, so 6 by 50 year. So these extreme droughts that extends for more than 3 years. The last one in Ceará lasted for 6 years. It's increasing also. Well, this decreased continental runoff enormously. I mean, this is the coastline of Brazil that many scientists call the hungry of sediments because it doesn't receive sediments naturally. And with these impacts from global change, reducing annual rainfall and increasing the extreme events, mostly extreme drought events, this runoff is decreasing sharply. If you see in this figure, this is the Jaguaribe River, which is the largest river of the Brazilian semi-arid, which is over 76,000 square kilometers of basin. I mean, it has decreased by from an average of 200 cubic meter in the beginning of last century, for instance, to less than 17 today. Obviously, this is not only the global change. I mean, damming of these rivers also help global change. So the things are accelerated. Another important thing, and then this morning, Professor Patrícia Ziveri has showed a very interesting graph about the accumulation of heat in the oceans and increasing marine forcing over the continent due to heat accumulation is another clear impact of global changes. And in a semi-arid coastline, this means that marine intrusion is going farther inland. Rivers, which has already its flux decreased by decreasing annual rainfall, cannot reach the sea, so it accumulates sediments in the higher estuaries and also accumulates pollutants, because pollutants are brought in from the continent. So instead of migrating directly to the continental shelf, it is retained inside estuaries. And you can see easily the impact of that is a huge expansion of mangrove forests because there are many new areas that they can colonize. And here you can see in the right lower level the impact of ocean heat accumulation when you see the ocean waters migrating to the continental shelf and from the continental shelf pushing inland the estuarine waters. Next one. Well, this just a picture confirming the pluriannual trends of decreasing annual rainfall in the basin and the increasing concomitant increasing of mangrove area. The next one, please. The next. Well, most of the source, I mean, there's the first slide, this is quite similar to the first slide Paulo showed. This is the agulhas leaking of very heating Pacific water or Indian waters into the Atlantic, and it reached northeastern Brazil. And this probably is a very important driver of augmenting the residence time of freshwater and continental runoff within the estuaries. And this is a very important aspect that I'll show you in the next slides, please. Apart from this, there is one other thing that is occurring. Most of these ecosystems are completely out of their normal state. I mean, they are not functioning as they should. So most of these ecosystems, which like mangroves, but also seagrass, that can act as a barrier to pollutants from the continent to the sea, are leaking, literally. I mean, they are losing their support capacity, the capacity of accumulating substances. This is an example of 2 mangrove forests in the semi-arid environment, showing clearly the loss of this important ecosystemic value, which is accumulating eutrophication nutrients like phosphorus. I mean, a healthy forest can accumulate up to 96% of all the phosphorus coming into the system, while an stressed environment can accumulate less than 50%. So this is another reality that we have to take. I mean, when global warming affects, it will find ecosystems like this, not the ecosystem that we used to when I studied ecology, maybe 50 years ago. The next one, please. So taking into this in consideration, you have 2 things occur in the semi-arid, linked to hydrology and pollutant accumulation. The first one, the dry season is increasing in time. I mean, you have more and more months without rain or wet seasons with rainfall much lower than the historical mean. This hydrological modeling in terms of pollutants, it's very simple. I mean, during the rainy season, when you have those pulses of high water, pollutants are exported directly to the continental shelf. So since they are coming from the ocean associated with particles, they are basically non-reactive. So they are exported, sedimented, and stay in the continental shelf. Since sedimentation rates are very low, they tend to be buried in the continental shelf. So they have very low bioavailability and pose a very small environmental risk. But during the dry season, then it's different because the river cannot reach the sea. I mean, it's blocked by ocean forcing and an immense decrease of river flow due to lower annual rainfall and damming. Under this situation, most of the estuary is flooded, and the continental runoff spends a long time in the estuary before being pushed out to the ocean. So you have time and condition for increasing the reactivity of pollutants. And remember that most of this area in the tropical semi-arid are colonized by mangroves. So this is another important aspect because the biogeochemistry of this area is very particular because it's based on sulfate reduction that produces a lot of dissolved organic carbon because it's not able to oxidize completely the organic matter. And this keeps a lot of pollutants soluble and therefore bioavailable. And it stays there. It doesn't go to the ocean till the next rainy season if it's strong enough to push out everything. Otherwise, it stays cycling and being available to incorporation to the biota. The next one, please. Here are some examples of the biogeochemical process involved in the increasing bioavailability of, in this case, mercury, but it also happens to some other pollutants, especially POPs. You can see easily that a mangrove still acts as a retainer of, in this case, mercury. It incorporates a lot of the mercury that comes in with the tide, but what it releases is a reactive species of mercury. Because you see in the 2 graphs on the left, an increasing in mercury organic complexation. And this is a very important thing because organomercury complexes are much more bioavailable than inorganic mercury or particulate mercury. And you can see easily that this dissolved fraction is the dominant fraction during the dry season. That's the green for the dissolvent and the black for the particulate. And during the dry season, nearly 100% of the mercury present in the environment is dissolved organocomplexes, so extremely bioavailable. The next one, please. And you can see the reflect of this in the continental shelf. During the wet season, which is the graph below, you can see that you can explain all the dissolved mercury concentration, or at least the majority of the dissolved mercury concentration, with the particulate mercury concentration, meaning that mercury reached the platform associated with particulate mercury, particulate material from the continent, and part of this mercury dissolves and stays soluble, mostly forming chlorocomplexes. But when you go to during the dry season, you can't see any correlation between particulate mercury and dissolved mercury. In fact, dissolved mercury is exported by the estuary, is the major species exported from the estuary to the continental shelf. So the estuary starts exporting not particulate forms, that is very low bioavailability and will end up easily in the sediments. Dissolved organic complex, because this is associated with carbon, as we saw in the last slide, is not only bioavailable, but keeps in solution. So it can spread the contamination, like you saw in the Amazon, when you spread it through the gassing here, we spread it by chlorocomplexation. And you can see in the figure that the Jaguaribe River is actually exporting mercury contamination along shelf. The next one, please. And the impact is also very easy to see when you compare the same species of animals thriving in the lower estuary, marine-dominated area, where all these processes are occurring, with the higher estuary, which in principle would be where you have more concentration, because the pollutants come from the continent. So the higher estuary is closer to the source, so it should present higher concentrations. But as I said, it has to stop in the estuary to become reactive. And then what you see is that the bioaccumulation, which is much better than only concentration, shows easily that this mercury in the lower estuary is orders of magnitude more bioavailable than in the higher estuary, as a result of the process that I showed in the last two slides. And this is for one species of shrimp, but it occurs in, please go back. Yeah, it occurs in also all other species that you can measure in the lower and higher estuary. And worst, the effect is already passing on humans. This is the calculated or estimated risk of mercury exposure to different populations along the estuary. And you see that the population live on the marine sector of the estuary, where those processes are occurring, present an associated risk of exposure, which is over 5 times higher than the population in the fluvial part of the estuary, notwithstanding that they are closer to the sources again. The next one, please, which is just finishing my talk. The next. Well, this is a very short appraisal. We don't have time to talk too much. I think I have already talked too much, as usual. But I would like to thank some people. I mean, this idea that came out as a new ecological theory that has been published recently is not only my own, especially thanks to Professor Rosane Marins, who coordinates the laboratory that I work, and Professor Francisco Dias. They both played a key role in developing this theory that we call the Arctic paradox. I think you already understood by showing the slides. I mean, in the Arctic, you increase mercury inputs to the ocean, increase pollutant. Here, you decrease mercury input to the ocean, but also increase pollution. That's the paradox. And this is because this reactions in the lower estuary. So I'd like to thank you all again. And what would be my final measure, which is beware with the Anthropocene, because their technology won't work. I mean, we're not going to controlling sources. Those sources are uncontrollable. There's no clean technology. Not because it's not available. It cannot develop a clean technology for this kind of source of pollution, which is remobilization from old sources. So that would be my message to you to end my talk. Thank you.
Thank you very much, Professor Drude, for your awesome talk. You're covering so many aspects and link between the global warming and the remobilization of pollutants, and also shows some examples of the so great importance Amazon River in extreme environments like the semi-arid region. We will follow now with the presentation of Paulo, because the connection of Paulo is established. Then we will follow with you, Paulo. I think that now it's okay.
Okay. Can you listen to me?
Yes, I am listening to you.
Great. So I will jump to the end of my presentation, just to save the main message, and with that we jump to the discussion. If it's okay for you, like that.
Or I think you can present your talk, no? You think
Okay, I
I
will start in this point, and
okay.
just because I think I was following the Drude presentation, I completely lost Vanessa, unfortunately. But many topics that I am describing, considering other examples, was considered by Drude. So I will jump to this moment. So here we are. Rhodolite pads, they are through the Brazilian continental shelf, from very, very shallow to deeps around 100 meters. So they are quite important calcifiers in our system. And they are built by these coralline algae that sometimes live free in the bottom, providing beautiful oases of diversity that we have in Ceará. Of course, we have everywhere in Northeast, and of course, they occur here in Brazil, up to the Florianopolis island, more or less. So, when we expose these rhodolites, trying to remember my point is that, we are providing the combination of different stressors in this complex scenario that we have in coastline. So we have climate change, global stressors, combined with local stressors, pollution, and continental runoff, as Drude said very, very well. So all of that is changing the chemistry of our oceans that is warming very fast. So we have these rhodolite beds in this entire coastline from Florianopolis to Amazon mouth that are receiving waters more warm during the heat waves, mainly, of course, and more fertilized by nitrogen and phosphorus, as Drude said too. So we have a runoff very rich in these fertilizers because we have agriculture and urbanization, as I said in the beginning. So with that, we have rhodolite bed losing the capacity that they have to sink carbon and carbonate. So they have this combined very important capacity to control the biogeochemistry of our oceans. So they can sink carbon from CO2 from using photosynthesis, and also they can.
Hey, Paulo, sorry.
Yes.
Just a reminder. Can you put on the mode of presentation, because you cannot see all the presentation. No.
Oops. It is. I would change something here. Sorry. It is okay now? How it is working?
Yeah, it's better now. Yeah.
Is it working well?
Yes, and
I don't have a clue about how to make disappear this. If you want, I can start again.
no, it's okay.
Sure? Okay. Okay, so they lose capacity to I will put this here, to sink CO2 and to trap nitrogen, for example. So of course this happened differently in different species, but considering Lithotemnium crispatum, a very important species that is present throughout the Brazilian coast from Santa Catarina to Amazon mouth. So this species will really lose a lot of its capacity to sink nitrogen, sink CO2, and carbonate. So they are losing. So we are losing a very important environmental service that these rhodolites provide to us. And of course, as we are saying to the broad audience, the rhodolite bed we have in Brazil, they represent a kind of human heritage because they really should have a planetary importance considering the climate balance that we are. So we are losing this very important ally to help us to fight against the climate change. Okay. Well, another point to consider is that climate change are changing the behavior of our web traffic web, and changing this functioning, we are losing some services surplus. In other words, we can lose, for example, in this case, Wally was a master student that evaluating the herbivory of main seaweeds we have in our coast. We observed that our sea urchin, under ocean acidification and warming, start to increase the feeding rates, mainly under acidification. So considering acidification, as you can see here in this black bar, in the end of the experiment, in the third week, the sea urchins start to eat much more than considering our control situation, that is the almost 400 ppm of CO2 and 24 degrees. So yes, acidification, the CO2 when diluted in the water can change not just the seaweed behavior, but also the invertebrate of this invertebrate that is a quite important herbivores that we have in benthic communities everywhere, as we saw this morning in the presentation, in one of the presentations that we had. Well, why that? Maybe because under this condition, the seaweed lost capacity to provide energy to the urchin. So to compensate the stress provided by the chemistry, the water chemistry change, the sea urchin is changing its behavior, eating more and more seaweed. That will play an additional stress to this benthic community, reducing the canop as we observe it in this region of the Brazil. I'm not sure if that slide was one of the slide that you lost, but we observed a huge loss of canop cover in the Brazilian coast in the last 4 decades. So we don't have the forest, the underwater forest that we had before. We are losing very fastly. 40 years is nothing considering evolution evolutionary time. So yes, something is happening, and it's happening quite fast. In the last 10 years, we have observed in the Central Atlantic and sometimes in northeast of Brazil and north of Brazil, these huge blooms of sargassum. Here we have this picture in the bottom, the sargassum amount in beach in Maranhão state. So something is happening because, well, we have likely scenario involving more CO2, higher temperatures, and a different runoff with more nutrients, because the ecosystem that we have in our coastline are losing the capacity to sink the CO2 and also the carbon. So everything is available to this planktonic environment, and algae are blooming everywhere. And this bloom of sargassum, this golden tide, are producing a huge impact in the Caribbean, as we can see in this modeling, in this niche suitability evaluation that we did. Is a recent paper of one of our PhD students of our lab, Lidiane Gouveia, where we show that the high biomass we have and everything else, the distribution too, is associated with dissolved nutrients, high temperatures, and salinity, low salinity. In other words, the runoff, the continental runoff, is related with the bloom of sargassum that is producing huge damage in the Caribbean, mainly in the Caribbean, considering social and environmental losses, very, very deep losses. So we are with a big problem in our hands. As Drude said, we are losing capacity of this coastal vegetation or coastal forests, in other words, mangroves and salt marshes and seagrasses that had before a very important role sinking CO2. They are losing this capacity, and of course we are losing these formations, and with that we have much more CO2, much more nutrient in the water, in the coastal water. And with that, I think that is hypothesis, one important hypothesis that has been discussed everywhere and all the time we have, that the coastal area is working as a bioreactor, producing huge biomasses of sargassum. So the question is, okay, sargassum is growing, producing a huge impact in Caribbean and part of Brazilian coast. But here we have a solution, a very interesting solution to our main problem that is represented by the CO2. Once sargassum is growing too fast, it is sinking CO2 and taking CO2 to the bottom of the ocean, to very, very, very deep areas, 4,000 meters, for example. With that, sinking definitively CO2, considering the time scale that we need to mitigate climate change. If we take this in advance and use it as a tool to mitigate warming and climate change, maybe we can manage our future better, considering this important learning with a natural phenomenon that now is producing a huge problem. We evaluate the amount of carbon and organic matter that we have in sargassum bloom, or that we can have in sargassum bloom if well managed. We can sink more CO2 than the observed in the all mangroves we have in our planet. In other words, the amount of carbon that we can have in sargassum is huge. So the eutrophication desertification that we observe and cause huge problems can represent some inspiration to solutions. And talking about solution, we are doing right now exactly that, just to provide a take-home message. I think I disagree a bit with Drude, considering that maybe we can work harder and harder and harder, and maybe try to provide some solutions to new generations. And algal turf scrubber is something that we are developing in our laboratory. Is something that can sink CO2, sink metals, and of course produce a way to increase or improve the water quality of our coastal areas. But to provide this kind of thing that we by now is just something that we built in the laboratory scale, we need a multilateral perspective considering this kind of biotechnological tools, and also the rebuild or the restoration of our natural systems that naturally during time was with a very, very important role to sink nutrient and CO2. I'm talking about, in this case, considering seagrasses. Seagrasses sink all of that and also increase the water quality, increasing alkalinity to provide calcification of some organisms. So if we combine, here is the results considering the net primary production of alodoli and Alimeda, for example, considering the scenario of acidification. And here we have that with acidification, and when Alimeda is with alodoli, we have an important change in the calcification capacity. As we can see here, calcification is this graph in your left up corner. Here we have Alimeda cuneata with alodoli right, with a normal capacity of calcify or to produce carbonate than we have in our control. So if we manage to restore our environments, invest in technology, maybe we can try to put our system back to this center of sustainability. Here we have different stressors. Many of them are under control. We are much far from the planetary borders or the planetary limit. So we are using too much fertilizers. We disturb the biosphere integrity. We are living in a climate change scenario of uncertainties. So we need to put it back in some places where the social foundation can or should be sustained, but with respect to the ecological feeling of it. So this is the Dennett theory, and here we are developing some tools using algal solutions. So algal-based solutions can help us to this challenge to keep, of course, our environment safe, but considering an articulated process to provide sustainability with social integrity and with respect to the economy. Well, we need to think that social integrity is more important than it. So yeah, maybe this represent the alternatives of layers that we should consider when we start to discuss coastal management or integrated coastal management. In this year is the year of local elections, and I think that we can't forget it in our discussions, in our academic discussions. So policy options, they are dependent of our politic options, and our our past show us that when we ignore it, is a we are facing a big mistake. Well, we are facing big mistakes right now. So, final consideration, marine forests are threatened by local stressors and global change, warming and acidification. We are losing coral reefs in Brazil. We are losing seaweed forests. We are losing seagrasses and all the services and goods they provide us. We need to invest much more to understand the microbiota and the complex impact on food web that all these stressors have. And to do it, we need to work together. I think this is an event that represents a bit of how we need deal with it. We need work with a multilateral perspective. For example, combining different efforts from Italy, from Brazil, from different places in Brazil to go further and further and further. This peak we took from an experiment we did in Antarctica. Wow, I think we need think outside the box, and maybe something that we did there, and maybe I think we have a whiteboard. You see, as you can see in this short peak, we are nothing in this big world, and we need to respect it and maybe try to reduce our ecological footprint to the next generation, have a planet to live. And that's it. Well, I presented here some couple of results of different colleagues, students, staffs from different institutions. And I think this is a kind of environment that can foster the necessary discussions to produce the solutions we need to a different country and to a different planet. That's it. Thank you very much.
Thank you very much, Paulo, for a nice presentation covering so many aspects of the environmental problems that you have and they are increasing. And of course, you need to think about solutions. But if you have only problems, we don't have a good way to follow. But of course, you need to think about solutions. And now I think you can start our discussions about the four talks and the three talks, sorry, and some aspects that are talked here. I will start just it's just one question. It's really two questions for Drude. I will start with you to pose this question. It's one question for Sergio Rossi, and I will mix with other question because Sergio Rossi asked about one graph that you present, and he asked about could the ice melting of the Arctic be responsible for the mercury circulation accumulated between the 60 and 70 years? And the other is about why there are so amount of mercury present in the Amazon forest soil, and what are the causes of this accumulation of mercury in Amazon? These are the two questions.
Well, in the Arctic, the icing, it may indirectly affect mercury circulation in the ocean because it affects the equilibrium between atmosphere and the ocean. It affects the gassing of mercury. I mean, the gassing increases. So it increases the speed of mercury cycling. So that would be a way the icing would affect. The other is that most of rivers in the Arctic are actually blocked by the ice. So if the ice season shorter, so in the early summer, there is a huge de-ice in the area, you release very fast everything that has been accumulated within the rivers. There is a very interesting work about this phenomena. The ice acts as a plug, and it controls the residence time of the water in the marginal lakes where methyl mercury is produced. So if you facilitate the export of methyl mercury by de-icing and deplugging the rivers earlier, then you enhance the export of methyl mercury to the ocean. That would be the basic two things. One linked to the equilibrium of the gassing of mercury from the ocean to the atmosphere and vice versa. And this has been proved, at least in some areas, an increase in mercury deposition because of that. And this plugging effect of the ice in the mouth of major Arctic rivers. In the case of the Amazon, what you have is very old soils. These soils, 1 meter of Amazon soil, the typical high density terra firme forest, 1 meter of these soils can have between 6,000 to 12,000 years old. So this means that the mercury there is the result of a 12,000-year accumulation of mercury. And you see in that graph, during the Holocene, you could have depositions of mercury which is higher than what you have during industrial times because of increasing aridity, increasing soil dust production to the atmosphere, and other aspects that you don't need to take in detail, but I can later send some things to you. But in the end, what you have is a huge accumulation of mercury from natural sources in these soils. And due to podolization, which is a very strong and particular soil formation process in the Amazon, it's typical in the tropics, there is a complexation of this mercury 2 plus, with very refractory organic compounds. So once deposited in these soils, this mercury will very seldom be remobilized and exported. Once you keep the forest, because the forests keep on providing the organic matter to the soil and the conditions for organic matter accumulation in the soil. So if you keep the forest, you have a system that maximizes the accumulation of natural mercury. All the natural mercury comes from the atmosphere. There's no basing rocks in the Amazon reach or enriched in mercury. In fact, it's very poor. You saw in that graph, that graph is a little bit complicated, but if you make a balance of the mercury, nearly all the mercury that comes into the forest stays in the forest. In a similar way than happens with nutrients. There's no other way for the Amazon to survive. If the forest is not able to extract efficiently all the nutrients from the atmosphere, it can survive. So all these mechanisms that are very efficient in keeping the nutrients inside the forest, in avoiding the nutrients to be leached out of the forest, act equally to mercury. So you have plenty of mechanisms to accumulate and decrease the export and the loss of mercury from the forest to the rivers or the subsoil or anything like that. So you have a huge accumulation there. Normally, typical Amazon soils has from 5 to 10 times more mercury than the average global background. And that is it, and it's there. It doesn't go into the trees, it doesn't go into the tapir, it doesn't go anywhere. It stays there in the soil, immobilized. But once you take out the forest, then things start happening. First, increasing UV radiation. That's very important for the mercury chemistry because it accelerates the transfer from mercury 2 to mercury 2 plus, the oxidation. After that, there is a sharp decrease in pH to the range that methyl mercury is very likely to be produced. Second, you have huge temperature in the surface. I didn't show it, we don't have time, but we have measured the gassing rates of mercury in many different situations in the Amazon. And the gassing from pastures is maybe 2 to 3,000 times higher than inside the forest. So once you hit the forest, like you saw, you see the amount of mercury accumulated in a pasture soil and in the forest soil. They are close. I didn't talk too much about that, but you see in that slide, there are people walking in the field. I mean, the pasture and the forest, they are close. In fact, the pasture soil, some 10 years ago, were huge forests. So the amount of mercury should be the same in both soils if nothing happens. But when you see, you have lost the majority of mercury from the pasture soil, up to maybe 60, 80 centimeters deep. So all mercury accumulated during the past 10,000 years is remobilized after a soil exposure due to deforestation. So the amount of mercury being remobilized is much more than any gold mining is producing there nowadays. I mean, in the past, there was a lot, but not today. I don't know, not today. I always talk about that. I mean, but we have this kind of time scale of old people is changing. Yeah, so I normally say, no, deforestation rates are not that high. But I'm not talking about the 2 past years. I mean, the 2 past years, everything increased. I mean, deforestation, soil loss, everything in a rate that we never conceived possible. But it was. I mean, we never thought about Brazil becoming I don't know, 10th world country, but we are nearly there. So a huge amount of mercury is being remobilized today. Levels in most of fisheries keep increasing, although there's no longer any point source like gold mining at the same level as before. And people carry on being contaminated. And many recent studies has demonstrated a worsening of physical and metabolic conditions of the local riverine population because of mercury. And, what are you going to do? There's nothing to close. I mean, you cannot go there and close a tap in an industry and avoid mercury coming into the environment. There's no other way. I mean, we cannot control global change. Actually, we're not controlling global warming. So things will, it's not like Paulo said, maybe I'm a little bit pessimistic because of, I don't know, old age or whatever, or seeing the things happening all along again and nothing happens. But the thing is, in this specific aspect, we have nearly no control. We cannot control sources. Our technologies are not applicable in this global scale yet. I mean, we cannot avoid people from the Jaguaribe River estuary or the Madeira River to eat fish. Therefore, it's a very, very complicated situation. I mean, the best thing we can do is a very good monitoring, which is expensive, so unthinkable in the times Brazil is passing nowadays. But monitoring, and after monitoring, some kind of adaptation, because mitigation, I mean, the system Paolo Orta showed is very interesting. I mean, I've been talking about doing this in the shrimp farms in the Northeast since I arrived there 20 years ago. For me, it's very, very obvious. But I'm thinking of an ecologically driven mind, not a profit-driven mind. So that's impossible. So, in fact, sustainability is a concept that is based on profit, and then it's crazy because nature cannot be thought that way. But this is another thing that we can discuss many hours.
But that's important. That's quite important.
Yeah, but I keep on talking too much. This kind of questions that Sergio asked, I mean, just normally drive me for hours of speaking like a crazy old guy. Sorry.
No, it's okay. It's other problem of deforestation. So many problems related to deforestation. This is other, and it's crazy, really. Okay, follow to the next question. It's Sergio Rossi also, but this is for the Paulo. And I will mix one question of myself because it's about the carbon budget, carbon sequestration. We know, for example, that rhodolite, they make calcification and they capture the dissolved inorganic carbon from the water. They make the skeleton of calcium carbonate, but they they also emit CO2. Then this is my question: in this budget, what is the most important? The production of CO2 or the sink of dissolved inorganic carbon? And the other is and Sergio asked also how much it's about the sequestration of carbon, and what's most important, the seagrass or the rhodolite to make this carbon sink? Can we know it about it?
Unfortunately, not yet. That's a very, very important question, but we are really working on it right now. We have a common friend, Nadine Schubert, that now we have is a postdoc in Algarve University. Yeah, Nadine will present it to us maybe in 1 or 2 years. But by now, our hypothesis is that, yes, well, we have primary production and calcification. The calcification, you're right, release a bit of CO2, but the primary production of the rhodolite and that came from the entire community sink this carbon. This is something that we are observing everywhere when we do incubations with rhodolite beds. We put rhodolite beds in a plastic bag, for example, with everybody that come with the rhodolite beds, and what we observe in the end is less carbon than in the beginning. It's simple like that. So they are sinking during the day a lot of carbon, and this process is faster and more important and abundant in the system during the entire year than the release of carbon. So the balance is, we have in rhodolite bed autotrophic systems that are sinking the organic and the inorganic carbon together at the same time. I think we have chemical questions considering the seabed chemistry. The carbonate amount and the saturation state is higher, and this induces precipitation, more and more precipitation. Well, we have many hypotheses that is now have been working. Nadine have been working on it, and considering the other question, seagrasses and rhodolite beds, man, that we don't know yet. But we are losing a lot of seagrasses. So seagrass beds is something that sometimes we don't find anymore, at least here in Florianopolis or in some place that I know in São Paulo or in Bahia. So yeah, we are losing this kind of blue carbon environments. And without these environments, man, we have a problem. What is happening with rhodolite beds? We don't know yet, too. So we have many questions. And again, it's important to invest in science. We need to dive on these questions, really dive on it to understand better what is happening right now and what we need to do to increase our capacity to manage all these functions and eventually our future. Anyway, that's it.
Okay, yeah, it's a one open question.
Yeah, completely.
Amount of carbon in all the costs. So if you put the mangroves together, salt marsh, and well, it's a lot to do.
Just one question. We did that. We did with sargassum because sargassum is floating. So we have nice satellite images from satellites, and then we did this modeling very well. So we are really right now doing the same strategy with rhodolite bed. So we will have some clues about your question in the next 2-3 months, but by now, nothing.
Okay, let's wait. One question now to Vanessa. It's from I don't know the name. It's Equan Sustainability. I think that is one ONG. Vanessa, how much we know about the impact of trace elements on the primary production of our coastal shelf? This is the question.
We know very well the impact of trace elements for the primary productivity in general terms. We know how the system reacts if you add more trace elements or if you are lacking trace elements. But in the continental shelf of Brazil, we have practically no data. Okay, it's as I tried to explain in the presentation, it's super hard to determine trace metals in seawater. Brazil has only one clean sampling system nowadays. It belongs to Felipe Nencheski, the FURG, and it's the only reliable way to collect clean water. Otherwise, you can work, with GoFlow box, GoFlow bottle, with Teflon, and you can do very local studies, but you cannot really evaluate the coastal shelf or anything like that. So we have a really huge problem in terms of infrastructure and vessels, Brazilian research vessels, to actually work with ocean chemistry. So we can do nutrients, nice, we can do rare earth, but we cannot collect water in our ships to evaluate trace elements. So we don't really have reliable data for the shelves. There are some, but I honestly have serious doubts about it because we don't have, or they were measured not in 100% clean conditions. So very few labs nowadays in Brazil can produce this kind of data. So there's a lot of work to do still.
Yes. A lot to do. And I will just link this question with another from Rossi, because he asked about some idea about how climate change will transform the balance of these trace elements that are essential for primary production. Then this is some ideas about this.
Some trace elements like iron, they are deficient in, let's say, 30% of the surface of the ocean, could benefit for an increase in temperature that can increase the solubility of iron that comes mostly in the ocean from dust. So there are studies that show it. But some other elements you can change the speciation with, deoxygenation and, small changes in pH, and they can become less available. So you can change the bioavailability of these metals with all this change in the chemistry of the Mother Ocean. But so far, we haven't really experienced it. There's some work from Frank Milero that evaluate a whole bunch of different metals and how they will behave in climate change conditions, but I'm not really sure. Iron, we have a really good indication that we're going to have, we may have a positive effect in some areas because it's a very limited nutrient for several areas. But for the other elements, like zinc, for instance, or cobalt, we are not really sure. Not yet. I don't think so.
Vanessa, can I compliment just a bit? Just because one of the results of Ligiani's work, the modeling stuff, was the indication that iron was really very strongly correlated with the bloom of sargassum in this tropical area of the central and north Atlantic. And one thing that we have been pushed by different authors, even in these big journals like Science, that the Amazon runoff should be related with this increase of nutrients like iron and of course nitrogen and phosphorus as usual, but iron is something different that Ligian is bringing up. And I have one question to Drude. I don't know if it is possible, but
yes,
Vanessa,
for sure.
as Vanessa said, yes,
For
iron
sure.
is correlated with this bloom of sargassum. But one of the things that we observed in these tons and tons of sargassum observed in Caribbean, for example, is arsenic. Can be the arsenic. I saw the Ecoando Sustentabilidade is a program we have here in Florianopolis from our students. I think it's one of our students for that, the question about primary production, Vanessa. But any guess about the arsenic content in sargassum that he really very high in Caribbean, just because this is a health problem there? Can be the arsenic related with the runoff from the Amazon River or Tocantins? This is another important river that I think the Brazilian people should highlight the importance, just because this is crossing all the crop production in the Northeast. Huh?
Drude, seu microfone está desligado.
You're talking about arsenic.
Yes.
Yes. Arsenic. Well, the Caribbean region is particularly enriched in arsenic. There is a range of volcanic activity through Nicaragua and down to the outer islands of the Caribbean. And this is probably a more significant source of arsenic. There is also the large contribution from Colombian rivers that also came from areas with high arsenic, except that in those mining stations along the close to Cali, I don't remember right now the name of the valley, they use arsenic in mining operations, gold and silver mining operations. But I don't think it's enough to reach the larger Caribbean. I mean, it's much probably an effect of this ring of volcanic activity coming from Nicaragua and down to the outer Pacific Islands. It's probably a more important source than anthropogenic sources.
Yeah.
Okay.
Thanks a lot.
Yes. I have one question from André Carrara Morandini for Professor Paulo. Do you think it's possible to evaluate different levels of importance from small to large scale diversity, and how can we move forward to fight this biodiversity crisis? This is the question for Dr. Paulo.
Man, this is another
André.
From André. Well, André is a good friend.
André
Morandini was my friend during the graduation, undergrad colleagues. So 20, 30 years ago, more or less. But anyway, nice to see you this morning, André. Without hair, in fact. But let's see. Well, we are facing one of the biggest problems ever. Biodiversity crisis is quite correlated with the planetary crisis that we are living. Losing biodiversity, we are losing environmental services that, as we show it, Drude, Vanessa, I lost your presentation, sorry. But I try to show you a bit. They are quite important to provide the equilibrium that our planet needs. So how to change it? I think we need to change people's mind, considering the model of development we have. I think we need, in this moment, this pandemic moment, COVID killing thousands or millions of everywhere, I think we need to think better in what is really important to each of us and reduce our consumption. And we need, of course, increase the quality of our consumption too. And I think it's like that, thinking locally, acting locally, changing things locally to reduce the impacts that we are producing locally, but globally are changing everything. The Anthropocene is that, is a kind of huge meteor that is coming down everywhere all the time. So if the human being represent the meteor of this sixth extinction, max extinction, it is not a big, just one big meteor. We have many different kinds of meteor. I like a figure of language that used to say that we have a bomb in our hands, a big bomb in our hands, that we just don't know how long is the staff to increase the bomb capacity, and when the bomb it will come up and explode us and all the diversity we know. And well, I think this way, acting locally, teaching people about the importance of biodiversity, about the importance of our oceans. We have the ocean decade, but if we don't change our reality, if we don't change the politicians we have, for example, and this year is a quite important year in Brazil, we have the chance to change the things starting from the bottom. Well, if we don't change it, we will never really show people about the importance of biodiversity. We need to change that, because changing the politics, we will change the education, we will change everything in a kind of cascade effect, changing, in fact, our future. But I believe I'm not optimist, I think, but I have hopeness, and working hard with hopeness, I think we can change something. Well, let's see.
Yeah, I think that you need to act right now. This is change some habits, and we don't have. We have one question for Vanessa, and they ask about the microplastic pollution. How to control the microplastic in the ocean, and what are the future aspects in your opinion?
Oh, well, I'm very far from being an expert in plastic, and Monica Costa will give a talk tomorrow.
Yes.
But what we need to do is to control sources, basically. We have continental sources, and we have oceanic sources with, all the fishing activities, all the ships that goes everywhere. So in the continent, we need to think the 5 R's, reduce, rethink, recycle. We cannot, buy anything in plastic anymore and use it once and throw it in the bin. So we have to make a better use of it and design or use only materials that are more durable. So we stop creating more plastics. The trouble is that plastic is super useful, for so many applications. There's nothing around that is as cheap, as durable, and as flexible that we can substitute. But the only way to reduce it's basically controlling sources, both, from the production and industrial side, and from our side, from society, and have a better destination from all plastics we use. But watch it tomorrow, the talk from Monica.
Yeah.
She's going to address this issue
For sure.
particular. Yeah.
We have a comment from Nicolas Duvalli, I think is for Paulo. He said about the curious difference from the rhodolite beds of the Atlantic to the Mediterranean is that in Atlantic there are more species of coralline algae, and while in the Mediterranean there are few. I don't know if you want to comment something about this.
Yeah, that's true. I think the coralline algae is using an evolutionary and ecological niche availability to build a different kinds of biogenic reefs in South Atlantic. In fact, we have very few species of coral reefs or coral hermatypic corals, but in other hands, we have in a work that should be published soon from one of our students, Marina Cicini, we have more than 70 species of coralline algae in the South Atlantic, just in shallow areas. If we add to this list the possible diversity that we have in mesophotic regions, man, we should have, in fact, a huge diversity of the seaweeds in Brazil, of this kind of rock forests. Is interesting. It's a rocking. It's something that rock and roll. Sorry, the joke.
No, it's okay. Yeah. I think we have more few time just to complete this section. I think I will repeat one question from the morning that I think was very nice, the answer of the speakers about the main message of the three speakers about, do you think about the main message and related to the situation that you have right now and in future, more related to the impacts in the coastal in the ocean? I think we can start with Vanessa.
Oh, well, if you think about pollution and the way forward for the ocean decade, we need to control sources. And talking about Brazil, especially, we need to have wastewater treatment. In the way the situation it is nowadays, we will never have, coastal waters, clean rivers, clean, and the health of our population, especially the less privileged, will be really bad, as always is, because it's just too much pathogens, too much pollutants, and we have to deal with that in a better way. We need to clean our waters. We need to treat our sewage.
Yes, Paulo, your main message, please.
Well, I think the main message is we need to understand better the situation we have in our coast, in your area. I mean, just the big picture we are presenting here, maybe ignore the specific problem you have in your region or in your city. Understanding better the problem, and maybe sewage treatment is something that is huge, is a problem everywhere, should be considered. The occupation of land, I mean, all coastal forests are under threat right now, considering the CONAMA, well, bizarre Monday that we observed some weeks ago. But what we have in our regions can introduce in our policymakers priorities, or to our policymakers priorities and targets to work to solve the problems and to provide solutions for the alternatives that the social and the environmental perspective will need. So yeah, we have a lot of problems, but we have the science with us, and people that still believe that science is important. I think most of the scientists of Brazil still believe in science. So let's continue to work and put our work in favor to our society, to our environment. That's the take-home message. That's it. And thanks a lot. It was a very nice experience, despite I died in the middle, but it was nice.
Okay, thank you, Paulo. Drude, your main message, please.
I'll try to be elegant and quiet. No, I think the changes that we thought would starts occurring in the end of the century, 2050. I mean, all the scenarios that is modeled by all the reports from IPCC, for instance, are already occurring since maybe 50 years ago. And now we are living with them. I mean, you living now in Ceará, in Northeast, you see that these problems are real and present danger, like the Romans. So we don't need to wait them to occur. So I think we have to think about adaptation. When I first became acquainted with the IPCC through the Brazilian Panel of Global Change, we talk a lot about mitigation and assessments. Nowadays, obviously, you still have to go a lot on assessments and think about mitigation, like Paulo has brought some example, like Vanessa talked in her final talk about controlling sources. Obviously, we have always to think of ideal world and the world that we live, that people still poo on the beach and there's no treatment for sewage. But even thinking about a nice, pretty, clever world, we have to think about adaptation. And to think about adaptation means, one, to accept that the changes are already occurring. Yeah? We obviously are human beings, so we always try to postpone the problem. So the IPCC works the same way. So if you say that, well, in the next 20 years, you cannot raise the temperature for 1.5 degrees, and then 10 years later, you already overpassed this mark, then you put maybe 2 degrees and maybe 3 degrees. Maybe in the IPCC are 10 or 12 people will talking about we cannot reach 6 degrees. So that's the first thing we have to do. We have to stop being humans like that and act. Obviously, we have to carry on with assessment and mitigation, but adaptation is very important. And a correlation with that is that we have to rethink our concepts on dealing with nature. Otherwise, we're not going to make any good adaptation measurements. For instance, I think it's more than time to discuss the concept of sustainable development. Sustainable development was proposed in 1972. It was fantastic. Yeah, I was already a student there, and then, that lady from Ovation was a god. I mean, fantastic concept. But then it was a world maybe over 70% of the people still dies with hunger. We didn't have large maladies controlled and things like that. So that view was not wrong. But nowadays, I mean, still think about sustainable development, thinking about profit. Thinking when you talk about sustainable development, say, well, a well-being for everyone. But what is this well-being? I mean, is buying more things? Is everyone having electricity or having a car or whatever? So maybe it's time to rethink the concept, and then really go to adaptation policies that are real, that are feasible, and that we will change the basic needs of the people. Obviously, it's very difficult, like Paulo said. I mean, to talk about those things in a situation that we'd see now in Brazil. I mean, that's crazy. I mean, we're talking about mitigation, and the guy is just cutting down all the environmental regulation. We're talking about local people, and people are killing local people. Well, there's a kind of mitigation strategy, and very successful. You kill them all, and then you don't have the problem. Fine. So I know it's difficult, but as scientists, we have to think otherwise. I mean, like Paulo said, we have to think about science. And I think, based on science, that first, changes are already occurring, and not only today, but occurring at least for half a century. The effects cannot be controlled, even if we stop everything. And then you have to adapt. And to adapt, I think we have to review some concepts. I mean, adaptation will only be feasible if our concepts of mostly sustainable development, but others, has to be rethinked. Otherwise, conservation efforts, recuperation of areas can go mean nothing in the near future. So I hope not being too pessimistic. You know.
Well,
Well, thank you for the opportunity, and I hope we can meet again in the near future.
Well, I would like to thank you very much, the three speakers. I think it was really, really nice, the presentations, the discussion, and we are advancing in time. Then I just would like to thank you very much. Just a final advice for all participants that to make the register, to register the frequency, you need to log in at the website of the event. Then thank you very much, and I think that we arrive at the end of this section.
Thank you very much
Thank
for the
you.
opportunity.
Okay, bye.
Bye-bye.